if you study calculus long enough, eventually you're going to encounter differential equations. If you're going to study engineering, you spend a lot of time working with differential equations. In a nutshell, a differential equation is an equation that describes a rate of change. So they usually have the form dy over dx equals some function of x and y. When the differential equation involves the first derivative and no higher derivatives, that's called a first order differential equation. And that's what we're going to tackle. In fact, we're going to tackle a very specific type of first order differential equation, which is one that's called separable. So in order for a differential equation to be considered separable, the function f of xy actually has to be a product. So something like dy, come on, man. Where's my little dy over dx equals like g of x times h of y. In other words, some x stuff times some y stuff. And when they are set up that way, there's a technique that we can use to solve these. The goal for these differential equations is to come up with the function that, had that derivative. So we're working backwards. Let me just scoot over to another slide, but I want to take this idea of x stuff times y stuff and then show you, in general, how we solve these things. So let's get a new slide going here. So as I mentioned, these separable differential equations are, g of x times h of y, some x stuff times some y stuff. The technique that we're going to use to solve these is to collect all the x stuff on the right and the y stuff on the left. So essentially what we do is we divide by the y stuff on both sides. That is terrible writing. And we multiply by the x stuff, just the dx here. We just want the dx over there, right? Okay, so this cancels and these cancel, and we end up with, dy divided by y stuff. That's still some y stuff, or 1 over some other y stuff. We have y stuff here with the dy, and x stuff here with a dx. And then what we can do is we can do the indefinite integral on both sides. And when we do that, we'll get some other y stuff and some other x stuff. And then they both have a plus c, but we just combine the plus c into one big old plus c over here. We've talked about how c works before, where you can take two plus c's and add them together and it's still just a plus c. I don't want to go into detail on that now, but we'll collect that constant term over in this big red plus c over here. And that's the gist of it, right? Eventually we'll solve for y, and we'll get y equals if there's anything else we need to solve for. But that's going to be our goal. So this little line right here, integrating both sides, is the key to this. I used a lot of vague, weird notation that no math person would ever use on this slide. Let me just go to some examples, and I think it'll make more sense. So in this problem, which is from the handout that you're going to work on, we're asked to find the general solution of the differential equation. The general solution means the equation with the plus c. So this just means the plus c, and we're going to solve this differential equation. So this is going to be a separable differential equation because it's the only kind I've shown you how to draw. So our technique is going to be to get the x stuff on the right and the y stuff on the left. Okay, now, it doesn't look right now like this is a product, right? You have to remember your rules of exponents. This is actually the product of e to the x times 1 over e to the y, right? E to the negative y is 1 over e to the y. And usually I write this as 5e to the x over e to the y. Okay. When you see it like this, we can easily use multiplication and division to separate the y stuff on the left and the x stuff on the right. Holy cow, speak English. It's like 5:50 in the morning when I'm doing this thing. That's my excuse anyway. So what I'm going to do is multiply by e to the y over here. And that'll give me e to the y dy over dx equals 5e to the x. And then remember I said I was going to multiply by dx, so I'll do that too. I'll do a dx here and a dx here. And when you do that, you end up with e to the y dy equals 5e to the x dx. So I started with this differential equation. I used rules of exponents to rewrite it, right there. And then I started using multiplication to rearrange the terms so that it looks like it's separated and ready to do our technique. Once you have the terms separated, I have y stuff on the left, I have x stuff on the right. All I'm going to do is integrate both sides. So the antiderivative of e to the y is just e to the y. And the antiderivative of 5e to the x is just 5e to the x. And then don't forget, we said we're going to take both of the plus c's and combine them over here as 1 plus c. Okay. What I'm going to do is separate the screen here and just rewrite that so I can finish this off. So this is the same thing. I'm just rewriting it again so I can work here. Okay. Our goal is to solve for y. And I hope you'll remember that when you want to solve an exponential for the exponent, you use natural log. So now I'm just going to do the natural log on both sides. Let me just, I'll sneak it in there. So I'm basically going to do this and do this. And the natural log of e to the y is just y, which is excellent. And we don't care what the natural log of 5e to the x plus c is. We're going to leave it. And this ends up being the solution we were looking for right here. Okay. So we start with a differential equation. If it's a separable differential equation, we can use multiplication and division to separate the y stuff on the left and the x stuff on the right. Then we integrate both sides, and then we do a little algebra to solve for y. That's the gist of it. Let me show you how we use this technique to also solve an initial value problem. So you can see in this problem, we do have a differential equation, and it is a product of r and y. Note that here we just changed the variables. R is the same as x. And next to it, we're given an initial condition. When r equals -1, y equals e. And that's going to help us essentially solve for plus c. We're going to figure out what the c equals. First, we need to solve the differential equation. So we have this dy over dr equals 2r times y. I can divide both sides by y to separate this and multiply by dr. And remember, the y's are going to cancel and the dr's are going to cancel and end up with 1 over y dy equals 2r dr. Once you get the terms separated, you're going to do an integral on both sides. Antiderivative. So you got to remember that we've done the antiderivative of 1 over y. That's natural log absolute value of y. And then the antiderivative of 2r is just r squared. And then remember, we're collecting that plus c over here on the right. And our goal is to solve for c. Let me just draw a line here. So the way you solve for c is you just substitute. So I'm going to rewrite this equation, but instead of putting a y in the absolute values, I'm going to put the value of y, which they said was e. And instead of r squared, I'm going to do -1 squared. And then from here, I should be able to solve for C. The natural log of the absolute value of E, that's just log E, that's 1. Negative 1 squared is 1. So this just tells us that C is 0. Okay, so that means we can rewrite our equation as natural log absolute value of Y equals R squared. And remember, we solve these by doing natural logs. We already have the natural log, excuse me. We're going to use exponentials to solve this, so it's going to be E that we use. So on this side, we're going to end up with Y, and on this side, we're going to end up with E to the R squared. Now, don't freak out too much about these absolute value symbols. Because R squared is always positive, E to the R squared is going to be positive, and that means RY is always positive. So essentially, in this case, we can ignore those absolute value bars. We didn't actually ignore them. We considered them, and we realized we didn't need them. There will be problems where the absolute value bars are important, and when we get to that, I'll certainly make sure to point that out. But for the time being, if Y is always positive, the absolute value of Y is the same as Y. And E to the R squared is always going to be positive, so we're in good shape. Okay, I blew through these two examples. There are other videos posted for you to take a look at, but in general, we want to get the Y stuff on the left, the R or X stuff on the right, integrate both sides, and then if you're given an initial condition the way we were here, right, we were given this initial condition, then you're going to want to plug those values in and actually solve for the letter C, which is what we did right here. Right? We solved for C, and we figured out C was 0. Okay. Give these a go. Send me some questions. We're in good shape, and I think this will work out. So good luck. Take care.